Alright, so today we're talking about doped semiconductors. Now this is not doped as in, Lance Armstrong's semiconductors. This is something entirely different. Before we start, we should go through some preliminary info. Intrinsic semiconductor, which we'll be using, is referencing undoped semiconductors, so it's just silicon, nothing has been added yet. The number of free electrons is equal to the number of holes because we start off with only silicon, so it's a balanced element, and then if we have one freed electron, that means we will have one hole created. So the number is always equal to each other. And this is due to, it probably is not going to be in 0 Kelvin, so then it has heat adding it to the covalent bonds to break it apart. So there's always going to be a few covalent bonds that are broken to create free electrons and thus also holes. So we have on the bottom, you can see the silicon in a lattice structure. So there's 4 that are connected to the 4 valence electrons of a silicon. What is the doping process? It is the adding of impurity atoms in substantial amounts to increase the hole or free electron concentration of the intrinsic semiconductor. So it either creates p-type, which is the positive, which is adding holes, so there's more holes than electrons, or n-type silicon, which is more free electrons than holes. So on the bottom you can see example that we will have soon, which is the adding of phosphorus to the silicon to create a doping of extra free electrons. So in this example of doping, we want to increase the number of free electrons. So what we do is add impurity atoms, which we would choose as phosphorus because it has a valence electron of 5, which is 1 more than 4, which is the silicon's valence electron. And then the phosphorus takes the place of the silicon atom in the lattice structure. And since it has an extra valence electron, that electron is free to move around because it's not needed. So that electron is free to conduct electricity. Isn't there a positive, proton in the atom? Yeah, but it's bound, so it doesn't move as well. So then the electron moves, and then we would have the positive charge still in the nucleus. So then the net charge is neutral still. However, there are free electrons now instead of the silicon lattice structure. Now, some things to note. The doping of the semiconductor with additional free electrons doesn't change the number of holes. So you add more free electrons, but the holes still stay the same. So the number of holes that you had while it was an intrinsic semiconductor due to the heat, that number will still stay the same. Also, the majority and minority charge carrier are used to classify the concentration of electrons. So for example, in an n-type silicon, the electrons are the majority carrier and the holes are the minority carrier because you have more electrons that are free than holes. So for p-type, it'd be the opposite, where holes are the majority carrier and electrons are the minority carrier. And if you are curious as to why we use silicon in semiconductors, there will be a link right here to a video explaining that.